Okay, if you remember back to test 3, I think it was, we skipped problems that talked about the domain and range of a graph, and now we're going to add that transformations. I told you it would come up in test 5, and here it is. So what we want to do is look at the graph of f of x, which is the square root of x. And when you graph that in your calculator, it's going to look something like this. Okay, so that's f of x, the square root of x. I want to graph g of x, so I'm going to use a different color pen. And g of x is the square root of x plus 2. Okay, well, if we have a function and you have the original function, we'll just call it, we'll use the x squared function. Okay, here are the ways that things could change. Change that a little bit. If you have parentheses or something underneath the radical there, this changes the direction left or right. Any number added to the end or subtracted changes the direction up or down of the graph. So the transformation, if it's inside the symbol, inside parentheses, or in this case under the radical, that would mean it's going to move the graph left or right. Any number added to the outside of the parentheses, or in this case the radical, moves your original graph up or down. And this number in front that's being multiplied, that just changes the direction, whether the graph's going to be flipped up or down and how wide or skinny it will be. Okay, so when we look at this particular graph, we're adding 2 to the outside, which means it's an up or down shift. Because it's plus 2, it's going to be moved up 2. So the transformation from that original blue graph is going to be up 2 units. So I'm going to start at the origin and move up 2 units. And every other point would be shifted up 2 units. And that graph would look like this. So it's the same exact shape of the graph, only transformed up 2 units. Okay, now what about its domain and range? Let's look at just the graph of the red. Okay, so remember we need to discuss domain looks at the x's, that is left to right, and range looks at the y's. So looking at the domain, what's the smallest value of x that applies to this red graph? Well, you notice there's no negatives. It starts off at 0. So that would be from 0 to infinity. 0 is included, so we use the bracket. Infinity is not. Now look at the y's. Look vertically, bottom to top. What's the smallest value that y has in the red graph? You'll notice that the y value starts at positive 2. And then it continues on and on and on to infinity. Again, infinity always has a parenthesis, and the graph could actually equal 2. So we've graphed the g of x function, we've given its domain and range, and we described the transformation. So we've done everything that they asked of us. Let's try another problem just like that. Okay, we're going to look at that same graph, and I'm going to use red to graph that one. Remember, it starts at the origin, and it's just a little curve, something like that. That's what the square root of x looks like. Now, notice how this is under the radical. That means we're going to have a transformation left or right. So you have to determine which one. Well, when it's under the radical or inside parentheses, you always take the opposite. So the opposite of -1 is +1. So which direction in the left or right direction indicates positive movement? Well, that would be to the right. So the transformation of this graph would be 1 unit because of the 1 to the right, because you take the opposite of -1. So 1 unit to the right is the transformation. So I'm going to take this graph, I'm going to use a different color pen, and it's going to have the same shape here, but instead of starting at the origin, it will start 1 unit to the right, right there, and it will go that way. Okay, so it's the same kind of graph. Remember, you can put this in y1 and this in y2 and confirm that it does indeed move from this graph 1 unit over to the right. All right, now let's give its domain and range. We're looking at the blue this time. Okay, so what's the smallest value that x can have? Well, you'll notice that x starts at 1. Okay, the smallest value, it's not over here at 0, that's the red graph, it's at 1, so from 1 to infinity. It can be 1, it can't reach infinity. Okay, let's look at the range. Bottom to top, what's the smallest value that y can be? Well, when you're scanning bottom up, the smallest value is still 0, and the largest value would be infinity. Again, parenthesis always on the infinity, and it can reach 0, so it would have a bracket. So have we done everything? Let's check. We've graphed, we've stated domain and range, and we have described the transformations of the graph. So yes, we have completed everything. Okay, problem number 10. Let's read the problem. It says the period of a pendulum, remember a pendulum is like a grandfather clock, that arm that swings back and forth, so that's a pendulum, is the time required for the pendulum to swing back and forth to complete one cycle. So one back and forth movement is considered a complete cycle or a period. So the period in seconds is a function of the pendulum's length in feet, and it's given by f of L, that means the function of the length, is equal to 2 pi times the square root of the length over 32. I left this off of your notes, but what we want to do is actually find the period of an 8-foot pendulum. Okay, well, what do I have and what am I trying to find? The period is described as f of L. The length is L, and the length here is 8 foot. So what I want to do is substitute in for the L 8. So actually what I'm trying to find is f of 8, meaning that L equals 8. So let's substitute that in and then simplify. So 8 over 32 simplifies to 1/4. Recall that we said the square root of a fraction, you take square root of top and bottom, so square root of 1 over square root of 4. This is going to give you 2 pi. The square root of 1 is 1. And the square root of 4 is 2, so we'll put the whole thing over 2. The 2's here cancel. That's because you just multiply across up here, remember? And you get that the period is pi. Well, pi what? The period units is seconds, so the period is pi seconds. That means it takes about 3.14 seconds for this pendulum to complete one cycle of a back and forth movement.